Right, so here we go with CCEA, A2 Physics, Unit 2, Fields, Capacitors and Particle Physics for June of 2018. Let's get started. 8A Part 1. State Faraday's law of electromagnetic induction. So straight statement from your notes there. So the magnitude of the EMF equals the rate of change of flux linkage. Part 2. A circular coil of wire is placed with its plane perpendicular to a magnetic field. The magnetic field phi through the coil changes with time as shown in figure 8.1. Draw a graph to show how the EMF E induced in the coil changes with time on the blank set of axes, figure 8.2. So, we've got two things going on here. We've got the size of the EMF, and then we've got like Lenz's law giving us the direction of the EMF. So, the EMF is the rate of change of flux linkage. So, the EMF will be related to the gradient of this first graph, but it will be like the negative of the gradient. So in this first case we get a positive gradient, and that will generate a steady negative value here. Then we have no gradient, which will generate no value. Then we have a strong negative gradient, which will generate a strong positive value. And then we have a fairly gentle positive gradient, will generate a negative value. Now these are proportional to each other, so we need to pay attention to the fact that this is the most gentle gradient, this is the strongest gradient, and this is the sort of in-betweeny. So we need to be aware of that when we're drawing this. Okay, so we're going to start off with a value like that, negative corresponding to the positive gradient. Then it goes flat because there's no gradient for a while. Then we have a strong negative gradient, which gives us the strongest positive value, and then it changes to a positive gradient, which means it'll go to a negative value, but it has to be less than that first one we drew. So these are all representing the size of the gradient. So the strongest gradient's here, so that's where the highest EMF value is, and it's a negative gradient, so we get a positive value. This is a fairly gentle gradient, so we get a fairly gentle value here, which is less than this one because that is a weaker gradient than this, so that should be a weaker value than this. Part B. A coil of wire with 340 turns, each of area 65 centimeters squared, is placed within a uniform magnetic field of 55 millitesla. The coil is rotated through 500 revolutions per minute, inducing an alternating EMF within the coils as shown in figure 8.3. The EMF induced in the coil is 0.0 volt at times T1 and T2. By making reference to the position of the coil within the field, explain why it is 0 at these times. So these will be the positions where the coil is at 90 degrees to the field coming through. And that gives you maximum flux, but 0 value for the rate of change of flux. So those positions correspond to the position where the field is perpendicular to the plane of the coil, and in those positions you've got maximum flux linkage, but the rate of change of flux linkage would be 0 at those positions, and that's why you get 0 EMF. Calculate the frequency of the alternating output. Okay, so we need to bring back the details of the question here. So we've got 500 RPM, and we need to convert that into a frequency. So 500 revolutions, 500 cycles per minute, dividing by 60 will give us the cycles per second, which is our frequency. And that gives us 8.33 Hertz. Calculate the maximum EMF, and that's straight use of an equation from your notes. And so Emax is BAN omega. So we've got 55 millitesla. 65 centimeters squared in meters squared. Remember, there's 10,000 centimeters squared in a meter squared, so 65 times 10 to the minus 4. 340 turns, and 2 pi f, because ohms can be written as 2 pi f. And that's going to give us our EMF max. And that comes to 6.36 of a volt. Okay, thanks for watching.